So, we will start from last class. Last class we were looking at some variations that we have introduced in gas junction arc welding, right. So, we are looking at pulsed GTAW. So, instead of using constant current, by using a pulsed DC, so we may achieve some good the arc characteristics. So, for example, if you want to have a deeper penetration, so you need to increase the heat input significantly. So, then the I mean should be increased, isn't it? So, the mean current should be increased, but instead of using a direct or constant DC with higher mean current, by doing pulsing, so we can reduce the heat input, because for example, if you are welding at say current versus time, if you are using in a constant current, I mean, so you may have to increase the heat input in such a way that you can increase the penetration, or you can improve the arc characteristics. So, instead of using a higher I mean, so we can use a pulsed current. So we start with a background current where just enough to keep the arc ignited, and then to have a continuous arcing, and then in between you can pulse the current in such a way that we can generate much more stable arc with a high stiffness. Stiffness means the core, the arc core, where you have a plasma jet formation, can be widened. Okay, that means that if a plasma jet is widened, arc core is widened, then you will have a somewhat deeper penetration in the material. And by doing this process, if you calculate the average or current over this waveform, the I mean decreases significantly, isn't it? So, instead of using high current, and we can reach the higher penetration and good stable arc with a good stiffness by relatively low current. So, that is the advantage of using a pulsed GTAW. Okay. And this is also the pulse DC, it is also very advantageous in GMAW, gas metal arc welding, but we will see that when we are looking at the gas metal arc welding. But in this case, because of using pulsing, we can increase the arc stiffness much more effectively by doing pulsing with a much reduced mean current. That means the heat input decreases, but you will be increasing the penetration higher, right, because you are improving the arc stiffness, the arc core. Yes, it makes sense, right. So, the pulsed GTAW can be used, and then so this is one improvement we have done into improving the arc. And the second one we are looking at is it's a variable polarity, square wave ACs, isn't it? Square wave AC, and then variable polarity DC. So, in this case we looked at in the last slide just before we completing. So, we have a problem using a sinusoidal wave AC. So, in a sinusoidal wave AC, so if you look at current versus time, so you will see in a conventional AC current, so you will have a sinusoidal wave, and this sort of a wave characteristic is not good for an arc. So, what I am saying here is, so in this case the current field is continuously changing, isn't it? So, for example, you start with one value, you go to an amplitude, the peak amplitude, but in this case the E what you looked at, the electric field density, it continuously changes when you are applying such a waveform. That means that the arc heat generation, the arc mechanism at which the arc heat generates, when you look at based on the E, it is also continuously changing. That means that the arc characteristics also change while applying an AC waveform, isn't it? And we also have a problem here. So, at one point in time the current always goes to 0, isn't it? So, that means that when the current goes 0, obviously the arc would extinguish. So, even if you have a very high frequency alternating current, at one point in time you always have a situation where there is no current to sustain the arc. That means that when you use a sinusoidal wave, the arc stability decreases significantly, because at this point there is no power in the arc because E is completely 0. Similarly, during this process the current is not constant at all, it is continuously changing. So, you are increasing E and then decreasing E and then completely goes to 0, again it changes the polarity. So, such a waveform, it is not good for arc characteristics to keep the stable arc throughout welding process, because you are continuously changing the heat input as well when you are changing E. So, in order to avoid this problem, so we can use a square waveforms, that is much more beneficial. So, instead of using a sinusoidal waveform, thanks to the modern power sources we looked at, rectifier inverter or the transistor based power sources. So, instead of having a sinusoidal waveform, we can have a square waveform. So, in this case, so instead of having a sinusoidal, so we will have waveforms that are generated in such a way that instantly we go to the peak current and then we maintain the current. So, that is good for the arc stability. So, the E is maintained at constant, and then we can reverse the polarity obviously by using a proper transistor systems, or and then we will keep the arc constant, because rapidly we are decreasing it. And then when we can also tell the power source, when the current becomes 0, obviously we can supply a high voltage to reignite the arc continuously. So, the arc stability increases significantly, because the moment it becomes 0, we can also we can know that when the current becomes 0, then we superimpose a high voltage ignition to ignite the arc, and this process can be made into extremely rapid. Whereas in the previous, in the sinusoidal wave conditions, it is not possible, because there is a range in which the arc is going to get extinguished when it goes below background current. Whereas in this case, we avoid that problem. So, by having in a square waveforms, right. So, we increase the current in such a way that we keep the mean current constant over a period of time and reverse the polarity. And during this process, when we can also know that when current becomes 0, we can superimpose a high voltage surge in the system to keep the arc ignited all the time. So, this is much more advantageous than using a simple sinusoidal wave. So, when you are using an alternating current for welding, in most of the cases modern power sources give square waveforms. Okay. So, that is the most common waveforms, because of the advantages what I am trying to tell, right. And the same can be applied to the variable polarity DC as well. So, instead of using a simple single polarity, for example, for GTAW, what is the most commonly advisable polarity for GTAW? Electrode must be negative. So, DCEN is the most common polarity what we generally use, because you do not need to overheat the electrode. Okay. So, the electrode is always cathode, which is connected to negative terminal. But sometimes if you are welding with aluminum alloys, so you need to change the polarity as well, isn't it? So, we can also generate the similar characteristics what you get in alternating current by changing the polarity rapidly by using a DC current, direct current. Okay. There are some advantages, because again, so the waveforms has to be corrected for alternating current, but if you are using a direct current, in order to have a complex transistor systems to generate the alternating current square waveforms, you can still have a simple DC current. Only thing is you can change the polarity. Okay. So, instead of having an AC current supplying transformer, so you can happily use only rectifier system, which can give you a reverse polarity to change the polarity rapidly, such a way that you will have sometimes an electrode negative, and then upon keeping for some time you can reverse its polarity such a way that an electron becomes positive. So, you can gain the advantage of the modern power sources, which can switch the polarity from electronegative to positive alternatively, and you can change the duration of the polarity change. For example, you want to achieve the good penetration. So, that means that you can use an electronegative, but you also need to cleansing action. But cleaning action, you don't need to keep it as same as the welding action. So, you can reduce the duration at which you keep the electrode positive. Okay. So, in such a way that you maximize the the electronegative, so that you will have good well bead penetration characteristics, and then you reverse it for shorter time, so that you will also clean it, right. So, that is beneficial compared to the square wave alternating current. Use an reverse or the variable polarity direct current with varying amplitude and then time at which you switch the polarity. Yes, is clear. And you can also change the current amplitude, in one case higher than the other case. So, the various possibilities are used to achieve required the welding characteristics. Yes, is clear. So, these are some of the advantages, and then we can also use both pulsing and then reverse polarity together, so that we can maximize the effect of the pulsing and its variable polarity. Yes, it's clear. And these are commonly used to weld very critical geometries and thin sheets. For example, sometimes you need to have a good geometrical accuracy by controlling distortion, because that is very important, right. So, because if you are welding in thin sections, the distortion effects are very high. So, in order to control the distortion, the pulsing, commonly we use the pulsing in DC for welding titanium thin sheets. So, square wave variable polarity DC can be used, because titanium also has sometimes oxides on surface, and as well as aluminum as well. Okay, so aluminum, welding aluminum, if you are using DC, you can use variable polarity direct current with pulse. Yes, it's clear. Good. So, we will move on to that. So, we looked at the pulse GTAW, the effect of pulsing. So, the important parameters are IP and then TP. So, we always keep the IP TP ratio constant for a given material. Okay, so we looked at yesterday. So, generally we keep the IP and TP constant for a given material, and we can work on the pulsing frequencies and the amplitude based on the material and the thickness need. So, these are the common the pulsing parameters we use. For example, pure nickel we pulsed 250 to 300 amperes, and stainless steel, copper nickel alloys. Copper nickel alloys are widely used for the marine applications, propellers, because they have very good corrosion resistance. Then plain carbon steels and pneumonic alloys, based on their thicknesses we can choose the currents and the pulsing frequencies what we need. Good. So, pulsing frequency can be increased to a very high frequency. So, we can go up to 500 hertz, 5000 hertz based on the power sources, and we found that the arc stiffness or the arc core characteristics improve significantly by doing pulsing. Yes, and we can achieve very high energy density because the core becomes enlarged. That means that the plasma jet you form at the center of the core can be increased in such a way that you will have a very good penetration, and due to that you will have you can also have the highest welding speed. Yes, it's clear, because productivity increases, because the arc energy increases, the efficiency increases. So, you can also increase the productivity. Yes, it's clear. Good. So, square wave, that is what I just talked about, the curve AC with variable polarity, and DC with variable polarity. So, basically what you do is we reverse the polarity in such a way that we keep it electronegative, so that we will have a good penetration, bead formation, and then we can switch polarity in such a way that if the electrode becomes positive, we will have a cleaning action, right. And we can change the amplitude of the current, as well as we can also give pulsing in this line as well to get the both characteristics. So, this is what we saw in last class. We will continue from there to other modifications we introduced in GTAW, and some of them are very widely used in commercial applications apart from the pulsing and then square wave. So, one of these modification, like adding filler to GTAW. So, in previous classes we saw the gas tungsten arc welding is commonly used in autogenous mode. Now, what is autogenous mean? Means you do not add any extra material, right. But you can also use GTAW with a filler. So, this is beneficial, especially if you want to make a fillet welds. Now, what is fillet weld? Means in overlap configuration. So, in this configuration, suppose if you want to join, it's most commonly, so we need to fill this gap, right. So, in this case, so we can use a fillet weld. That means that you can use a GTA torch and a filler, and then we can fill it. And GTA with filler is very commonly used if the weld is exposed or weld is naked, we call it naked welding. So, naked means no, we do not use any painting, and this is very commonly done if the weld is not painted, because then you can hide. So, if you are welding and weld is going to be naked, naked means no painting, so it is open. So, the aesthetically you need to generate very good welds. It should be very good looking at it. You do not feel like some porosity or spatters. So, in those applications, GTA with filler is the best you can get, because the aesthetic appearance of GTA welds are very nice. The productivity is very low, but you see some sort of stitching, some artist worked on it. So, it creates a very nice structure. So, any naked welds, the welds are not going to be painted and covered under the substrate surface. So, in those applications we use GTAW with filler. Okay. So, it is a bit tricky because the welder has to use both hands, because one hand he has to feed the filler, on the other hand he has to keep the torch. Okay. Generally when you are welding it up, we do a weaving action. Okay. It is not like you can't draw a line with the torch, because you will have to spread the liquid pool. So, you make a weaving action to fill the weld cavity, and also create an aesthetic applications, right. So, the filler addition in GTAW commonly used for fillet joints, overlaps and fillets, right. And if you look at the weld, very beautiful. See, this is one of the pictures I took in Spain. So, it is actually made in Philippines, but welding was done in Philippines, Spain. You look at this is GTA with filler. So, what I was telling about similar to fillet overlap configuration, and look at the weld. It is like a beautiful rangoli, isn't it? And this is done with an expert welder, but in this case when you are welding it, you should not be welding it in a single line, and you are not going to get a good property, because the fluid flow will not assist to make an aesthetically good weld, as well as properties will also be bad, because when you do in a single stroke you may also have undercuts, because the fluid flow may not be sufficient to fill the entire weld cavity. So, in that applications you have a TIG welding torch, and then add a filler, and then do a weaving action. Okay. So, the both hand should be coordinated in such a way that, so you create a weld with an overlaps like that. Yes, it is clear. So, this is very commonly used, as I said, when the weld is open, and you need to compromise on productivity. So, in this case if you use GMAW, the aesthetically GMAW welds are not as good as TIG with filler. So, GMA welds they are not as good as TIG weld, because in this case you just fuse melt the filler and then fuse it, and you can control the flow very nicely. It is like a cradle. Okay. So, you make a reciprocating motion with the filler, so that you make such a beautiful weld. So, now you don't need to do anything. So, in this case this is stainless steel filler, and I think this is stainless steel 316 pipe. So, one moment you fill it by the weld, and that is it, you do not need to paint, you do not need to worry about it. Okay. So, because it is aesthetically already very good, right. It is clear. Okay. So, the problem here in cold wire, the wire at room temperature is in productivity. So, we can improve the productivity by heating up the wire. So, the wire can be heated up, so that the temperature, you do not really reduce the molecular temperature by adding it up, adding a cold wire, and also if you are heating up, you also increase the productivity by melting more. Okay. So, the modification is again a hot wire filler. Okay. So, the advantage what I have talked about in cold wire filler is also here. So, it is like independent wire addition to control the well pool temperature, because in GMAW you filler itself it is melting. So, in this case you can control the feed rate independently, okay, because you are adding it. Okay. Most of the cases it is done manually because of the coordination. So, you need to have a proper weaving pattern achieved. It is very difficult to mechanize that. Okay. So, by having both reciprocating motion and then filler addition. So, generally done in manually, but only one system I remember they automated it is the Dabber guys. So, they made a mechanized wire feeder with reciprocating motion to have an appearance of a manually made GTAW with filler. So, as I said, the productivity of this process is very low. So, we can heat up the wire to reduce the temperature of the temperature reduction problem you see in cold wire addition, as well as wire can be heated up to higher temperature. So, you also increase the melting rate. Okay. So, the principle is simple, only thing is you need an additional wire the power source to heat up the wire, right. So, and then you need to make an automated wire feeding mechanism, because the wire can be heated up to temperatures where you can't hold it by hand. So, by creating the mechanism by which you can have a wire feeder, and then the power source which can heat up the wires to temperatures in a way that when you add the filler, you don't reduce the well pool temperature significantly. Otherwise, in previous case, you should also mind that when you are adding a filler, in most of the cases we add the filler in GTAW not to the arc, but to the molten pool. Okay. So, we do not add the filler to the arc, because then you can't control the melting rate. So, most of the cases, so this figure is also very clear. So, in this case we are not adding to the arc, right. So, we will add to the molten pool, right. So, this is very important, because when you are adding it to an arc, so you can't control the melting rate. Then the purpose of using GTAW is lost. You can very well use GMAW. So, you will not get aesthetically good weld, because then you can use GMAW, it is the same as using GMAW. Okay. And but when you are adding a cold wire to the molten pool, you also reduce the temperature of the pool. So, the temperature of the pool is also reduced. So, that means that it may solidify early, or it may solidify rapidly in such a way that you may end up having undercuts. Now, what is undercut? So, undercut is for example, you have a well cavity. So, you will have to fill the entire weld. Suppose if the weld is not filled and you have a geometrical discontinuity, and this is not good, because you have an undercut, and this will create a problem when your weld is applied with the load. Okay. Then you have a notch leading to a crack formation, and it will fail. And this happens because the weld solidifies and the liquid pool is not wetting the cavity completely, and if the temperature is low and it can solidify instantly and leaving an undercut formation. So, in this case the heating up the wire is advisable, because then you don't reduce the temperature significantly compared to a cold wire additions. Yes, it is clear. Any questions so far? Otherwise, we will continue. So, you can see deposition rates, change in deposition rates, comparing the cold wire and then hot wire, and this is hot and this is cold, and this is as a function of arc energy. So, what is arc energy? So, what is the difference between arc energy and the heat input? What is heat input? How do you calculate heat input in GTAW? Equal to VA by speed. Okay. And this is heat input or arc energy? To calculate heat input, You need to put an efficiency, isn't it? So in the most of the cases, this is a constant. Okay, so we may neglect this guy, and basically this is the arc energy, because that is the energy generated in the arc, isn't it? And how much is transferred, that is heat input, right? So you multiply that with the efficiency. We will see in GMAW in detail. So what are the relationship? Right now you can say, because we plotted the graph here, so it says arc energy. So arc energy is without efficiency. Yes, it's clear. So in GTAW you will have their own efficiency. This we'll see in subsequent classes. But now you can clearly see the deposition rate as a function of heating the wire and not heating the wire filler. Say for example, if you have an arc energy of 6 kilowatt, so by using an hot wire TIG, we can increase the productivity much higher, about 5 to 6 kilogram per hour you can melt. Whereas in a cold wire TIG, it's not even 2 kilograms. So the melting rate or deposition rate increases significantly by heating the wire. In most of the cases, we will be heating it up to 400, 500 degrees centigrade, the wires, right? So to high end. So anywhere between 200 to 500 degrees centigrade in hot wire TIG. Okay, good. It's clear, right? So how the productivity increases? Basically, you heat up so that you won't melt, you won't cool the melt pool as in the cold wire additions. And heating the wire, it also increase the productivity, because obviously you need to reach the melting point to melt the wire. The wire is already heated up, it melts quickly. Yes, it's clear? Good.